Hey, this is Dr. B. In our last slide, we talked about electron configuration. Let's add some details to it. This topic is orbital notation and the principles of electron configuration. The orbital notation will add some additional detail to where the electrons are around an atom. For example, consider lithium. It's a 3-electron system. Its electron configuration is 1s2, 2s1. 2 electrons in the first shell, 1 electron in the second shell, and this stuff up here is the orbital notation. Draw a box for each orbital and signify that the electrons are spinning in opposite direction by using an up arrow and a down arrow. Here we only have to draw an arrow in either direction since it's an unfilled orbital. The bottom part's the electron configuration, the top part's the orbital notation. The Pauli principle by Wolfgang Pauli states that electrons will always pair up in opposite direction spins within an orbital. Let's try it for oxygen. We have an 8-electron system. Electron configuration is 1s2, 2s2, 2p4. So let's draw a box. There's our orbital notation for the first shell, for the next orbital in the second shell. And the p system is a 6-electron system. Remember that? The orthogonal pairs of dumbbell-shaped orbitals. So draw 3 boxes on top of each other so you just remind yourself that there are 6 possible electrons. Now we have 4, and you might think that you could just fill them up like that, but you'd be wrong. Hund's rule states that we should spread them out as much as possible. Can you see how we can put 3 of them in separate, we could separate them out like that? And this is also considered consistent with the fact that oxygen forms 2 bonds. Hund's rule, spread them out as much as you can. Let's do sulfur. We're getting bigger now, up to 16 electrons. Ready? Electron configuration. 1s2, 2s2, 2p6, that's 10, 3s2, 3p4. Did we spread them out? Yes, we did. Are they spinning in opposite direction? Yes, they are. Is there an error? What the heck is this? Ah, there it is. I think I just forgot to put it in there. So that's the electron configuration with orbital notation for sulfur. Fine. That's orbital notation. It's not too bad. Now, when you go to big orbitals, by the way, when you go to the D, you want to draw 5 blocks. When you draw to the F, you want to draw 7 blocks. When you get to the G block, and we're almost there, you draw 8 blocks. Right on top of each other. Things getting really big. Okay. So we've got some principles and some rules. Let's summarize them. There is the Heisenberg uncertainty principle. We should mention that. You're not supposed to say an electron has a fixed location because it's not quite a thing. We always draw fuzzy regions where you show probability. The Aufbau order is the principle of always building up. We never would go from 1s2 to 2p1. We skipped a whole bunch of stuff there. We'd say 1s2, 2s1. Hund's rule says we should spread out our electrons, right? That's not correct. That is correct. And the Pauli principle is simply to put your electrons with opposite spins within an orbital, so that's wrong. That's right. Since this gets tedious, working your way out to, say, I don't know, Californium from 1s2, somebody came up with the bright idea of using a shorthand notation. The rule is it's okay to start with the nearest noble gas. So for magnesium, we don't have to do 1s2, blah, 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 blah. Why don't we just go from neon forward? Put it in brackets and then continue where you are. In this case, neon 3s2. For scandium, I think the nearest one is argon, which is at 18. 2, 4, 10, 12, 18. So that whole whatever is argon, and then continue. 4s2, 3d1. I should point out that when you're teaching this in a class, you very soon start saying, what does it end with? You know, you just ignore the stuff inside. And if you say, oh, it ends with 3d1, you'd say, hey, that's scandium, right? So that's the only part of it that's unique is its ending. It is, after all, an Aufbau order, a building up order. This is orbital notation and the principles of electron configuration.